Let's start with decision boundary b of k. So we want to find the minimum of this equation here for b of k and y of k. What we do, we take the derivative with respect of those variables. So we start of the decision boundary b of k, so we take the derivative of this equation in respect to b of k and we set it to 0 to obtain its 0 point. So what we can do is to solve the integral over two neighboring quantization intervals, because each decision interval b of k appears in two intervals, one where it is the upper boundary and one where it is the lower boundary. So we have here the lower boundary and we have here the upper boundary. So we're dividing the integral, solving it over two neighboring quantization intervals. And we come to the conclusion that we cannot get a closed form solution for a general probability function p of x. Yeah? So what we can do is that we can make the assumption that the p of x is approximately constant over our two neighboring quantization intervals. Yeah? So this is a very important assumption. This is how the algorithm is derived based on this assumption. So we are assuming that the probability p of x is approximately constant over two neighboring quantization intervals. Yeah? Therefore, when we don't have a closed form solution for a general probability function p of x, we will assume that it's approximately constant over the two neighboring quantization intervals. So we divided we're solving the integral over two neighboring quantization intervals, and we're assuming that the probability function is constant over two neighboring quantization intervals. Yeah? So then we can set that the p of x will be just a value of p, and then when we solve this equation here, we end up with this thing here. So we use this simplification. We assume that the probability function is constant over two neighboring quantization intervals, and we can solve this, and we have d of k divided by p is equal to this equation here. So what we'll do is to solve this using SymPy. So it's exactly this. So we just go from here to here using SymPy. So I'm importing from SymPy equation symbols, integral, derivative, simplify, solve. I'm defining the symbols x, y of k, y of k1, p of k here. Then I am defining here this integral, which is exactly the same as this integral here over two neighboring quantization levels. So we have from bk minus 1 to bk, which is this part here, bk minus 1 to bk, and then we also have the bk to bk plus 1. So when we solve, we have this, the tk is this here, which is just the expanded version of here. So we have this to the power of 3. If we expand here, we have the p here and this 3 here. So we have the p is here, so dk divided by p, and then we have this 3 here. So it's the same thing we just solved using SymPy from here to here. Now we have a closed form solution of this integral here that is given by this equation here, which is the same as what we've seen here. This is non-expanded form, and this is the expanded form. So what we need to do is take the derivative in respect to b of k, and the result is given by this equation here. So what we are doing now is we take this result here, and we are taking the derivative with respect to b of k, and we have this result here. So if we expand this, we will end up with this, which is just solving the derivative with respect to b of k using SymPy. So now we have this derivative, and we can set this to 0. So we will have this equation here, we will set it to 0, and we will find the b of k. So this means that we put our decision boundaries right in the middle of two reconstruction values. Yeah? This is, we assume that the signal PDF is roughly constant over two quantization intervals. Yeah? And this approach is also called the nearest neighbor, yeah? Because any signal value or data point is always quantized to the nearest reconstruction value. Yeah? This is a very important result of this strategy. So what we are doing now using SymPy is to have here, we have this, which is the derivative of the distortion with respect to b of k, and we're setting this to 0. When we solve, we have y of k divided by 2, this is the reconstruction value index k, plus the y of k plus 1 divided by 2, this is the reconstruction value k plus 1, so we have exactly the same thing. This is the decision boundary k and the reconstruction values y of k.